In this lecture, we are going to discuss about the wave equation. Suppose we have a very long pipe or string. It can carry waves traveling along. The position at any location here is the coordinate x. We describe the motion of a point in the coordinate as displacement of the point on the x-axis in space as w as a function of x and position and time. So it is the function of where it is and time, and the wave describes the motion of something that obeys the wave equation. The following equation partial square of w with respect to x square is equal to 1 over constant square into partial square of w with respect to time square. So it is known as one-dimensional wave equation. We are saying it one-dimensional wave equation because only one space variable is dependent here. This space variable is x or t. We can say this one-dimensional wave equation as one-dimensional linear partial differential equation. We can say it linear because here the constant coefficient is not the function of w, and also the higher power of w are not involved here. One-dimensional wave equations governs lot of incredible wide category of physical phenomena such as speed of sound, propagation across the room governs by the wave equation, light wave behave according to the wave equation, vibration of string, cable, long cylinders and pipes also governs by this wave equation. And vibration, longitudinal vibration of rods, torsional vibration of rods is governed by this wave equation. And the vibration in musical instruments is also governed by this wave equation. So it's worthwhile to know little bit about the wave equation, and whatever we did in the first lecture is kind of duality. You have things that vibrate with standing waves and mode shapes, but the same system can support the wave that travel along. So let's figure out why that is so. Now we are going to do the derivation for the wave equation for a string or a cable or long pipe. As we know that general derivation will apply to all the different things. So imagine if you have got infinite length string and it has this position. We'll describe as W as a function of x and time. It has the string has a tension T and a mass per unit length of string which can vibrate. So tension and length, and what other parameters do we need? So we are drawing it again at here in some displaced position, and what excited maybe vertex shedding, applied force causing the vibration. This force is due to the vertex shedding. So the excitation here can be written as force as a function of x and t. Here the force is per unit length, so its unit is Newton per meter. So now this string is fixed at both ends, and it is going to vibrate transverse vibration due to this excitation of the force, which may be due to the vertex shedding. So in that little there may also be the drag force of the fluid when this string will vibrate. So this drag forces of the fluid is known as damping force. So I'm going to cut out a little piece of this cylinder and do a force balance. So basically we are going to apply Newton's law of force balance on this piece of cylinder. So this cylinder is little bit curved on the horizontal. So this is our horizontal surface, and we cut a little piece of this string or cylinder. We need to evaluate all the forces acting on it. So the tension force is acting on each end, making an angle theta 1 and theta 2 with respect to the horizontal surface. So along the tension we have a excitation force here. There may be some resistance forces, we say drag force, damping. So this is the coefficient of drag, R of x or x, which is force per unit length times unit velocity, means per unit velocity times the force. On this we have to multiply the velocity, multiply it by the velocity, which is the derivative of this displacement W with respect to time. So this complete is equal to the force along here. Its unit is Newton per meter. So we will only consider the drag forces if we have the very highly viscous fluid. If a string is moving in a very highly viscous fluid. So here we have other things. We have four forces acting on this string. and this position is x, and this is the incremental position x plus dx. So little element is dx in length, and this is all for small motions. And if you assume small motions, then you can say that theta 1 here, theta 1 is approximately equal to the sine theta 1, and which is approximately equal to the tangent theta 1. So from the small angle approximation we can write this curved surface ds as a straight line. So if we assume small angle approximation, then it means that this tangent theta equal to the del w over del x. So we can write it theta is equal to the tangent theta. So this is the slope on the left side, and remember that we replace delta with the partial, because it's not only the function of x, it's a function of time as well. So we can write theta 1 is approximately equal to the sine theta 1 from small angle approximation, and we can say that it's also approximately equal to the tangent theta 1, and which is equal to the partial of w with respect to x. For theta 2, slope is changed a little bit. This is equal to the slope of the left hand side plus rate of change of the slope times dx. This is the slope on the left hand side, and plus rate of change of the slope, rate of change of the slope times dx. And this expression is from the Taylor series. We can write it as tau square w upon tau x square times dx. We can write it. Now we have simplified the theta 1 and theta 2, so we can apply the force balance on this small piece. So for this small piece of string, 4 forces are acting. So force on the right hand side is the tension component. We are summing the forces in the y direction. So in the y direction, the component of tension will be that component which is the t sine theta 2 and t sine theta 1 on the left hand side. So on the right hand side, t sine theta 2, and sine theta 2 is equal to the theta 2, and theta 2 is equal to this. So this theta 2 is equal to this term, and the direction of this tension force is positive because it is acting on the upward, and direction of this component which is on the left hand side, the tension component in the y direction, is the t sine theta 1, and its direction is negative. So we can write t sine theta 1 as sine theta 1 is equal to the theta 1, and theta 1 is equal to the, and theta 1 is equal to the partial derivative of w with respect to x. The direction of the drag force is downward, so we can take it negative, and the direction of the excitation force is upward, so it will be the positive. So we are multiplying it with the dx because this is the drag force per unit length. Its unit was Newton per meter, so we are multiplying it with dx. For the length of this element, we are multiplying its excitation force with dx. For the complete length of this element. So the sum of the forces on the object is equal to the mass times its acceleration according to the Newton's second law. So on the right side of this equation we have the mass and acceleration. We can simplify this force balance equation by taking the common the dx, and we can also, this will be, these terms will cancel out each other, so then we'll take the dx common. So these dx will also cancel out. So what we have left with this equation. So now we are interested in natural frequency and mode shapes. So for natural frequency estimations, the vibration must be free vibration. So we are going to neglect the excitation force, and if we are going to neglect the excitation force, there will be no drag force. So both these terms will be equal to the 0 for the calculation of the natural frequency. So this equation will become now in this form. We can write it as dou square omega with respect to x square is a partial derivative of w with respect to x square, which is equal to the 1 upon tension upon mass multiplied by the partial derivative of w twice the partial derivative of w with respect to time. So the quantity T over m turns out to be the speed of wave propagation in the medium. So we can write T over m is equal to the c square. So c is known as a phase velocity. Its unit is meter per second. It's the phase velocity of the wave propagation in the direction of, in the x direction. So here we have just find the wave equation for the string by doing simply apply the Newton's second law to the little section of the string. We can do something, cut out the little section of the beam, can do the same force balance on it, and for beam you get fourth order differential equations, and it's not the wave equation but it still vibrates. That's not governed by what we call the wave equation. So this is the one-dimensional wave equation. So for simple string, the speed of propagation traveling on a string is acquired by the tension developed per mass per unit volume. And if you had a long string and put the little plug in it, you see the plug running back and forth. And if I have a string, I put a little bump on it. So to get the natural frequency and mode shapes, basically we need to solve this equation. In order to find the solution of this wave equation, technique known as the separation of variable works. So here we say that w is a function of x and t, and the solution w of x is a solution of it, and g of t is also a solution of this partial differential equation. So here we are interested in vibration. So we are interested in what function of time that we will put in order that time dependent part remains same as anything else that vibrates. So for single degrees of freedom system, what is the time dependent function that we substitute in to find the natural frequency is exponential power of iota omega t. So we are assuming the solution of time dependent part is exponential I omega t, constant time exponential I omega t, and now we are going to put it in this We can also use sin omega t or cos omega t as a solution, but as we know that it is easy to find the solution of exponential function for differential equations. So we have assumed a solution for a wave equation, and now we are going to put this solution in our wave equation. Okay, when we put this solution of our wave equation, and by taking the partial derivative with respect to x, we will get this term. Here we take the derivative with respect to x, partial derivative with respect to x, and on the right hand side we take the derivative with respect to time. These terms will be cancelled out. Now W is no more dependent on time, so we replace tau with delta in this equation. So this equation, when we'll rearrange it, this equation, it will be the same as our equation of motion for undamped single degree of freedom free vibration. So here we see that we are left with an equation involving x only, and it's an ordinary differential equation. So the solution of this second order ordinary differential equation we did earlier, and we know that its solution, we assumed that x e raised to power iota omega t. So we can also take the solution of this wave equation as w as a function of x, which is equal to the any constant b e raised to power minus kx. So when we substitute w of x is equal to the b e exponential raised to power iota kx, then by substituting it in this equation we will get, and by taking the derivative of this with respect to x, we get this equation where k is equal to the w upon c. As we know that the frequency is equal to the 2 pi f angular frequency f is equal to the phase velocity upon lambda. So k is equal to the angular frequency upon phase velocity. We can write it as w is equal to the 2 pi f upon c, and we know that f of upon c is equal to the 1 over lambda from here. So we can replace this f over c with lambda. So we can write k is equal to the 2 pi over lambda, or k is equal to the w over c. So this term k upon phase velocity is known as a wave number. So k is called the wave number, and it also happens to be 2 pi over lambda, as lambda is the wavelength as sinusoidal waves going through the medium, and 2 pi over lambda is same as w upon c. So this is called the wave number, really important quantity. If you are trying to understand wave propagation in system, it is applied to the wave traveling down the beam. So the definition of wave number is frequency divided by the speed, or 2 pi over lambda. We cannot go much further with this. With just the wave equation itself, we have, in order to get the natural frequency, we have to invoke other information. We know in particular, in order to get the natural frequency, we have to create conditions for this to vibrate in a particular way. What we have did, we fixed the both ends and put some tension on it, and now it vibrates that clearly it had something at its ends. So this is boundary value problem. So we have to invoke the boundary condition to actually finish finding the natural frequency and mode shapes. Apply the boundary conditions. So the cable is fixed or pinned at both ends, so it means that at length x is equal to 0, the displacement will be So we are going to put the length x is equal to 0. So w of x will become 0. So 0 is equal to the b1 times cos kx plus b2 times sin kx. This is the real part and this is the imaginary part. So x is 0. So cos 0 is cos kx is equal to 0 and cos 0 is equal to the 1 and sin 0 is equal to the 0. So b1 is equal to 0 from the first boundary condition, and we are going to apply the second boundary condition. For second boundary condition, we are going to take the length x is equal to the L. So by replacing this x with L, so we have the term b1 cos kl and b2 sin kl. So from the first boundary condition, b1 is equal to 0. So we will left with b2 sin kl only is equal to 0, and that's true. That's only true if we put any one of that equal to 0. We put either b2 or sin kl equal to 0. So for a non-trivial solution, we cannot put b2 equal to 0. So we need to put sin kl equal to 0, and that's true, and that's only true if kl is equal to n pi. So now we found out that there is just for a vibration of finite length string is only particular values of k that works. So there it is special values of k which are in case of n which is equal to n pi over L. We now have a mode shape. We have a special solution to this w of x, and it only satisfies the boundary condition when it satisfies the boundary condition, and that will be the some undetermined amplitude bn come from the sine term. So omega w of x for this particular values of n is equal to the b n sine n pi x over L. So we can find the modes by putting the values of n. Then how we get the natural frequency? What we know that what is the definition of k? Definition of k is equal to the w upon c. So therefore especially particular values of k we allow solution to are going to be correspond to particular values of omega n. So for the particular values of omega n, and therefore omega n square is equal to the kn square in times c square. So we know that the values of k is equal to the w upon c. So kn square will be equal to the wn square upon c square, and we know that kn is also equal to the n pi over L. So we put this into this equation, and c is equal to the t over m, and we get the expression for the finding the natural frequency. We find the natural frequency in radians per second from this expression. So the first natural frequency is 1 over finite numbers 2L under root t over m, as n is equal to 1 for the first fundamental mode. So for the first fundamental mode shape will be like that, half of sine wave. So it is vibrating, so we can draw it like that, and so the sine wave is a full wavelength. It means it extends. This is the full wavelength, and that much is the half of wavelength. So if this length is L, So this is the length L, which means that lambda will be equal to the one complete sine wave, which is equal to the 2L for this particular problem. So how long does it take for a wave or disturbance to travel the length of this finite string? How long it takes to down there and return back? How would you calculate that? This frequency goes time to time through the distance 2L. What's the speed? The speed of propagation is c. So the length of time out would be, the length of our time will be the 2L upon c. Cos t is equal to the lambda upon c. So lambda is 2L. So the length of time is the 2L upon c. So the time required is 2L over c, and we can replace this c with under root t over m. So this 2L over under root t over m is what? The inverse of this frequency. So we can write this time t1 is equal to the 1 over fn. So for the period, there is a direct connection between propagation speed, frequency, and wavelength. They are very close to relate. So the natural frequency of the first mode of this string, that frequency is exactly 1 over the length of the time takes for the disturbance to travel down and back. So from the depth of understanding how the wave equation behave, you can guess the behaviors of lots of other things. In problem 8.15 of 5th edition SS Rao mechanical vibration book, statement is the vertical and horizontal forces, reactions and joint A and B of a typical cable of the suspension bridge is shown in figure 8.27. So this is the point, suspension point A and point B, and the forces at the joint A or B is a horizontal force of 2.8 into 10 to the power 6 Newton and a vertical force of 1.1 into 10 to the power 6 Newton. So these forces at pin joints, these are the forces at pin joints. And another information which is given to us is the cable are made of steel. Cable is made up of steel which has a weight density of 76.5 kN per meter cube. So it's a weight density. If the effective diameter of the cable is 25 cm, so diameter of the cable is 25 cm. Find the first two natural frequencies of vibration of cable in the vertical direction. So we need to find the natural frequencies of vibration. First two natural frequencies of vibration. So we will use this relation of finding natural frequencies, and we need to find it up to n is equal to 1 and 2. So here we have a suspension bridge, and we are taking two assumptions here. One is that the both ends of the cables are fixed, and we are taking the length of the cable equal to the span of the bridge, which is equal to the 500 meters. So in order to find the tension in the cable, we need to apply the Pythagorean theorem. So the tension in the cable is equal to the 3.0083 into 10 to the power 6 Newton. So in order to find the natural frequency of first mode, we need to know we must know about the tension, and second thing is we know about the mass per unit length. So in order to find the mass per unit length, we have the weight density, and we have the diameter. So we can find the mass per unit length of the cable or the density of the cable per unit length. We can find out this from this relation. As we know the weight density, we know the gravity value of gravity, we know the diameter of the cable, so we can find the density of cable per unit length. So density of cable per unit length is 382.7924 kilogram per meter. We know that C is equal to the under root T over M, where M is the mass per unit length and T is the tension in a string. So C can be also written as P over rho, where P is the tension and rho is the density per unit length. So speed of wave propagation is equal to the 88.65 meter per second for this cable. So finding the natural frequencies of the cable with and fixed, as we discussed earlier in the derivation. So we can find the natural frequencies of first and second knot, which is equal to the 0.55 radian per second or 1.114 radian per second. We can also find it in hertz. In hertz, the first natural frequency is equal to the 0.088 hertz, and second natural frequency is 0.17 hertz. So since wave equation is governed by the not only the vibration of strings or cable, it is governed by the longitudinal vibrations of rods and torsional vibrations of rod. So from the orthogonality of functions, we can predict the frequency equation and mode shapes for the longitudinal bars. So for both end rod with both end fixed, we have these boundaries conditions, and we will get the frequency equation similar to the frequency equation that we get for the string, and we will find the mode shapes and natural frequencies similar to the string. But if we have a bar with both ends free, we will have the same boundary conditions, we have the same frequency equation just like the string, but here we have mode shape of not the sine, it's the mode shape of function of cosine, some constant time cos of n pi x over L. So it means that these mode for this cos function, the wave will start from the extreme points. For the same wave equation is also governed by for the torsional vibration in the uniform shaft. So we can see that for the fixed shaft of uniform dia, we apply the same boundary conditions, and for finding the frequency equation is seem to be similar as for the case of string or of fixed rod in longitudinal vibration. So the mode shape will again be the same, and its natural frequency is also similar. Some important other physical systems that we care about, and the most I'm going to share one end, that the vibration of the beam. So here is a cantilever beam. Its first mode of vibration, tip moves maximum, can be looks like a quarter wavelength, roughly it's, but not exactly. So let's draw a cantilever. If we put a load P on a cantilever beam, it goes through the displacement. So this displacement is equal to the PL cube upon 3EI. This I is the area moment of inertia. In this case, our beam has a rectangular cross section and neutral axis in the center. So we can write I is equal to the integral of y square into differential area dA. So we can replace y square dA with the k square A, where this it is same thing with area moment of inertia. So we can write it area moment of inertia is equal to the k square A, where k is the radius of gyration. Now if we apply the force balance on this little element of this cantilever, neglect the external forces and damping, so the natural frequency and mode shapes, neglect external forces and damping, and solve for the natural frequency and mode shapes. So the free vibration with no damping equations look like this equation. In order to solve for the natural frequency and mode shape, we need to put this equation equal to 0, and that's the fourth order partial differential equation that describe the vibration of the beam, and you have to apply the boundary conditions. And for the string we have just b1 cosine and b2 sine, and for the beam it's b1 cosine plus b2 sine plus c2 cos and plus d2 sines. It means that four boundary conditions to solve for b1, b2 and so forth. A here is the area of cross section, which is equal to b times h. Rho is the mass density. Its unit is in kilogram per meter cubic. If we multiply it with the area and then with the small little mass associated with element dx, so times the acceleration will be the forces on the small little element, then solve this fourth order differential equation. So what will be the boundary conditions for this type of equations? If we talk about the boundary conditions for a free beam has zero motion at the wall, no strain at the end, no bending moment at the end, no shear force at the end. And if we talk about the boundary conditions of the fixed beams, then the fixed beam has no displacement, zero slope at both ends. So every different combinations gives you different natural frequencies. So we apply the boundary conditions for a beam. We find out that for all beams, omega n can be written as generalized as beta and nth of beta square under root ei upon rho times area. Here we know that I upon a is equal to the k square a. So I under root I upon a is equal to the k, which is the radius of gyration. So we can write it in this form, and this E, which is the modulus of elasticity upon rho is the density. So it is equal to the sound speed in solids, and so L represents the longitudinal sound speed for wave travel. And for the taut string we did earlier, the speed of sound wave propagation is Ct or C, and where this T represents the transverse sound speed. Here the term beta n varies according to the boundary conditions, equal to the Bn beta n square times KCl. So for the pin beam, beta n is equal to the n pi over L, and for the cantilever beam will be equal to the 1.194 whole square for the first node times pi square upon 4L square times KCl. So for the free beams, natural frequency is equal to the 3.0112 square for the first node times pi square upon 4L square times radius of gyration times Cl. Here is the speed of sound speed in longitudinal direction. Suppose this is a beam. This is a steel beam under no tension. So it means I can support it on its own weight. It can be a beam support waves traveling down the beam, the transverse wave traveling on the beam. We can support this. We can probably support waves. So waves are propagating at beams. We know that that's the fourth order partial differential equations, and how faster they go, that's the question. So if this yellow line is a beam and I want to know about the wave traveling here in my beam, so here a disturbance traveling along it with some speed known as Ct, which is equal to the under root omega times k times Cl. It's a transverse wave speed. So speed you are seeing across a wave running down in a beam. Here Cl is equal to the speed of sound in a material that propagates, and Cl is equal to the under root E upon rho. So this equation tells you about the frequency dependence of speed. It means that speed change with the frequency. If the frequency is high, waves go faster. If the frequency is low, waves go slow in a beam. In a wave equation, the speed of sound c is not frequency dependent, but all waves have on same speed. So for anything that obeys the wave equation, speed of propagation is a constant. If you plug in this string and let it go, that little shape will stay same and run up and down in the string forever. And that shape, you can imagine a plug like disturbance. You can imagine doing a Fourier series to approximate that. The shape remains constant due to the speed of propagation is constant for the case of string, but not so in a beam. If you did that, if you put a impulse into a beam, all the energy will stand out together within a very little time. A high frequency information get out in front of the low frequency information. So the that's called as dispersion. So beam waves are dispersive waves, whereas wave equation is not dispersive, independent of frequency. So here we complete our chapter number 8 for the continuous system.